We're going to go through an exercise for the Gaussian approximation. To examine the extent of validity of the Gaussian approximation, evaluate the expression, that's 8.7 given here, up to terms involving y cube. Show that this can be written in this form. The first exponential factor makes the probability p negligibly small whenever absolute value of z is much greater than 1. Hence, it follows that p has appreciable magnitude only where magnitude of z is less or comparable to 1, and in this domain the argument of the second exponential in I is much smaller than unity if square root of mpq is much greater than 1. Hence, this exponential can be expanded in a power series. Show therefore that p can be written in the form III. Show that the fractional error committed by using the simple Gaussian approximation is only of the order of square root 1 over square root of mpq, which becomes negligibly small to the extent that capital N is large enough so that capital NPQ is much greater than 1. Show further that in the symmetric case when p is equal to q, the correction term in III vanishes and the fractional error is of the order of 1 over mpq. Okay, so let's start with part A. So we have the binomial distribution P of n is equal to capital N factorial divided by n factorial capital N minus n factorial p to the n q to the capital N minus n. And if we write the natural logarithm of this, natural logarithm of p of n, this can be written as natural logarithm of capital N factorial minus natural logarithm of n factorial minus natural logarithm of capital N minus n factorial plus n natural logarithm of p plus capital N minus n natural logarithm of q. And then we can do this Taylor expansion, which is given in 8.7, when n is close to its most probable value n tilde, which is capital N times p. This can be written as natural logarithm of Pn around n is close to n tilde. We can first evaluate it at n tilde. Then we can take the first derivative d ln p dn, evaluate it at n equals n tilde multiply by y, and then we have plus 1 over 2 factorial second derivative ln p with respect to n, evaluated at n tilde y square, and then 1 over 3 factorial third derivative with respect to n, evaluated at n equals n tilde y cube, so on and so forth. So this is the expression given in 8.7. So here we have y is defined as n minus n tilde, and what we're doing here is a Taylor series expansion about n equals n tilde, the most probable value. Okay, so let's work on these terms one by one. D ln p dn, now using the expansion, the natural logarithm of p of n here, we can see that this is going to have the first term d ln capital N factorial dn, which will be 0. The second term will be minus the derivative of ln n factorial with respect to n. And then we have the third term minus the derivative of natural logarithm of capital N minus n factorial with respect to n. And then we have n ln p, derivative with respect to n gives us ln p, and capital N minus n ln q, that will give us a minus sign ln q. So this will be evaluated at n equals n tilde, and this must be equal to 0 because it's the extremum point. So maximum point where we should get n tilde is equal to np. So we're going to use the approximation for the derivative of factorial n factorial with respect to n for large n. So we can approximate for large n the derivative of ln n factorial with respect to n is approximately natural logarithm of n. This actually comes from Stirling's approximation. So ln n factorial was approximated to be n ln n minus 1. Since n and ln n much greater than 1, we can ignore the 1. And then if you take a derivative, you will get the first term ln n, and then the second term for d ln n factorial dn. So this is just a reminder, ln n plus n times 1 over n. So it would be ln n plus 1 and ln n much greater than 1. So this can be neglected. So we can write this as ln n. So this was one of the mathematical notes. You can watch the video 3.10 on mathematical note d ln n factorial dn. Okay, so you can review this. So we're utilizing this, so we can write d ln p dn is equal to minus ln n. For d ln n minus n factorial with respect to n, we have plus because of the minus sign in front and the minus sign in the parentheses, plus natural logarithm of capital N minus n, and then we have ln p minus ln q. So this evaluated at n equals n tilde should be 0. So this gives us the following result. Capital N minus n divided by n times p divided by q. This should be natural logarithm of this should be 0. So that should be equal to 1. So np minus np divided by nq should be equal to 1. So this is now n tilde because we have evaluated it at n tilde. So we find that capital Np minus n tilde p is n tilde q. So capital Np is n tilde p plus q, which is 1. So n tilde is np as expected. So the first term is basically 0 because it's evaluated at the maximum point. Now for the second derivative, now we're going to move on to the second derivative. Second derivative of ln p with respect to n. So if I look at the first derivative result, it started with minus ln n. If I take another derivative with respect to n, I would get minus 1 over n. And then the second term was plus ln capital N minus n. A derivative with respect to n would give me minus 1 over capital N minus n. The third and the fourth terms were ln p and ln q. They would give 0 because they don't have an n in them. So this term will give me, therefore, in minus parentheses, n minus n plus n divided by n times capital N minus n. These terms will disappear. So the second derivative is equal to minus n minus capital N divided by n capital N minus n. The third derivative I need, now I go to the third derivative of ln p with respect to n. This would give me, the derivative of minus n is 0 times n capital N minus n minus the derivative of n times n minus capital N minus n times minus n. So that will give me minus n times the derivative of n times capital N minus n with respect to n. The first term will be n minus n. The second term will be minus n. And this divided by capital N minus n square. So this one is disappearing because it's 0. Then I have capital N times capital N minus 2n divided by n square capital N minus n square. Okay, so now I have to evaluate the second derivative and the first derivative at n equals n tilde. So if I evaluate this at n equals n tilde, I will obtain minus n divided by np, then capital N minus np. So this will give me minus n divided by capital N square p 1 minus p. 1 minus p is q, and I have one of the n's disappearing here. So the answer is minus 1 over capital N p q. So that's for the second derivative. For the third derivative, evaluated at n equals n tilde, I obtain capital N minus 2 capital Np divided by capital N square p square capital N minus np square. So this is going to give me capital N square parentheses 1 minus 2p, and then here I have capital N square p square, and then capital N square 1 minus p square. So this capital N square will get rid of this capital N square, and here I will have 1 minus 2p. 1 is p plus q, so p minus 2p gives me minus p. So I have on top q minus p, and at the bottom I have a q here, so this is going to be npq squared. So I can substitute all of these into my Taylor series expansion. My natural logarithm of p of n in the vicinity of n tilde can be approximated as ln p n factorial, and then the first derivative term gives me 0 plus 0. The second derivative term is actually 1 over 2 factorial second derivative times y squared, so it's going to be 1 over 2. The second derivative evaluated at n tilde gives me minus 1 over m capital MPQ times y squared. The third derivative term is 1 over 3 factorial, that's 3 times 2 times 1, so it's 1 over 6. So I have plus 1 over 6, and the third derivative gave me in minus parentheses p minus q, it was q minus p, so divided by npq parentheses squared times y cube plus other terms. So if I define the parameter z as being equal to y divided by square root of capital NPQ, then I can write this result as natural logarithm of p of n in the vicinity of n tilde. The most probable value is natural logarithm p of n tilde, and then I have y squared over NPQ, so this is going to give me so I forgot the minus sign here. It was minus 1 over NPQ. So this is going to give me minus 1 over 2 z squared. And then I have a minus sign here. So it will be minus 1 over 6 p minus q divided by NPQ to the power 1/2 y cube divided by NPQ to the power 3 over 2, so that would give me a z cube term there. So this can be written as natural logarithm p of n tilde minus 1 over 2 z squared minus 1 over 6 p minus q divided by square root of capital NPQ z cube plus other terms. Okay, so if I take the exponential of both sides, so this is my natural logarithm of p of n at n tilde. Let's take exponential of both sides. This is going to give us p of n can be approximated around its most probable value n tilde, which I will call p tilde of n. This is ln p of n tilde is going to be e to the that value will be the most probable p value evaluation. Then I will have exponential minus 1 over 2 z squared term. Then I will have another exponential minus p minus q divided by 6 capital NPQ to the power 1/2 z cube. So this will be the end result, and here I have z defined as, if I write for y explicitly, I can say that z is defined as n minus capital NP divided by square root of capital NPQ. So that is what I have substituted for z. So let's go back to the problem statement. That's what I was supposed to show. So the probability can be written in this form. So this is the equation I and double I. So that's I, that's double I. Okay, so let's move on to part B of this problem. Now in part B, we're going to look at the z cube term. So the z cube term basically is the exponential minus 1 over 6 p minus q over square root capital NPQ z cube. So this term. So if you have the absolute value of z much greater than 1, that is n is much greater than np, we are deviating a lot from the mean value, the exponential e to the minus 1 over 2 z squared term will become 0 approximately. So I see that this term will become 0 approximately, and for z comparable to or less than 1, then we can consider the z cube term, because e to the minus 1 half z squared will not be 0. So we can consider it in this limit. But at the same time, if I have a square root of capital NPQ much greater than 1, if I define x as minus 1 over 6 p minus q over square root NPQ z cube, when square root NPQ is much greater than 1, since it's in the denominator, this is going to be very small. So if it is very small at this limit for the z cube term, I can use the following Taylor's expansion. So if you have e to the x where x is small, you can write this as e to the 0, first evaluate it at 0, then take the derivative with respect to x, evaluate at 0 times x, second derivative with respect to x, evaluated at 0, x squared, 1 over 2 factorial, etc. So this gives us 1 plus the derivative of exponential is exponential, evaluated at 0 gives us 1. So 1 plus x squared over 2 factorial, etc. So in this limit, I can use for the z cube term when the square root of NPQ is much greater than 1, I can write exponential minus 1 over 6 p minus q divided by square root of capital NPQ z cube. This is basically what I have called e to the x. This is 1, and then I have minus p minus q over 6 square root capital NPQ z cube. So this will allow me to write the probability as a function of n for in the vicinity of n tilde as p tilde, the z square term e to the minus 1 half z square, and for the z cube term, when square root NPQ is much greater than 1, I can write 1 minus p minus q over 6 square root of capital NPQ z cube plus higher order terms. So this is true for z less than or comparable to 1 and square root of capital NPQ much greater than 1. So what is p tilde? P tilde is obtained using normalization condition. And this was done in the lecture videos. So if you go through all possibilities of n from minus infinity to plus infinity, p tilde e to the minus n minus np square over 2 npq dn, and set this equal to 1, we find that p tilde must be equal to 1 over square root 2 pi npq. So this is done using the normalization condition. So you can find this in the lecture videos where we have gone through this calculation using the integral of a Gaussian. It was in one of the mathematical notes. So we find that eventually for the probability distribution around the most probable value and tilde, we have 1 over square root 2 pi capital NPQ e to the minus 1 over 2 z square, and then we have 1 minus p minus q z cube divided by 6 square root capital NPQ and higher order terms. If z is less or comparable to 1, square root of NPQ is much greater than 1. So this is our end result. So let's go back to part B. That's what we were supposed to show. This is the condition in expression that we have obtained for triple I. So this is the equation triple I. Now let's move on to part C, which is about the fractional error. So if I write P of n explicitly by distributing the prefactor into this parentheses, n equals n tilde, I have e to the minus 1 over 2 z square divided by square root 2 pi capital NPQ, that's the first term, and then the second term minus e to the minus 1 over 2 z square p minus q z cube divided by 6 square root 2 pi. Since I have two square root NPQs, this is going to be NPQ plus higher order terms. So in order to get the fractional error, so the fractional error I can obtain by looking at the difference between P of n for n equals n tilde minus the actual value when I substitute for n tilde divided by p tilde. So this is the actual value. So I find that this is going to be e to the minus 1 over 2 z square. The first term will disappear. This is going to give me e to the minus 1 over 2 z square one minus p minus q z cube over 6 square root npq plus higher order terms. So for z comparable to or less than 1, how does this behave? So this is going to behave as e to the minus 1 over 2 z square. So if I substitute, for example, for z is equal to 1 here, this will be e to the minus 1 over 2, 1 minus p minus q divided by 6 square root npq. So this is evaluated at z is equal to 1. So what is the order of magnitude for the error? For the error, I find an order of magnitude of 1 over square root npq. So error of the order npq to the power minus 1/2. So this is as expected. Now if I have p is equal to q, then the z cube term will disappear completely. The fractional error will become p tilde e to the minus 1 over 2 z square minus p tilde divided by p tilde, which is e to the which is of the order e to the minus 1 over 2 z square. And for z small, we can use e to the x is equal to 1 plus x square over 2 factorial, etc. So it is 1 minus 1 over 2 z square and higher order terms. So this is going to be equal to 1 minus 1 over 2. So if you go back to the definition of z, z was defined by double I, n minus n tilde divided by square root npq. So I can substitute for z n minus n tilde squared divided by capital NPQ, and I see that now I have capital NPQ here. So error of the order NPQ, capital NPQ to the power minus 1. So here it was capital NPQ to the power minus 1 over 2. Here the error is of the order capital NPQ to the power minus 1. Okay, so we have gone through this exercise to estimate the accuracy of the Gaussian approximation. So we started out with the Gaussian approximation. We expand the binomial distribution using the natural logarithm around n equals n tilde, the most probable value, Taylor series expansion, and we have used Stirling's approximation and derivative of ln n factorial with respect to n for large n to evaluate this, and we have found that really the most probable value should be capital NP, and we have evaluated the second derivative and the third derivative at n equals n capital NP, and by writing this explicitly for the second and the third derivatives and defining z as y over square root npq, we obtain the expression given in I. And for the z cube term, for z much greater than 1, the e to the minus 1/2 z squared term will become 0. So anyway, so this will go to 0. For only the absolute value of c less than or comparable to 1, the z cube term can be considered. And in that case, the square root of npq much greater than 1 gives us another simplification that we can write the exponential term that includes z cube as e to the x 1 plus x squared over 2 factorial, etc. So we can write it in this form. The p tilde term, the most probable probability value, is obtained using the normalization condition, and this was also done in the videos where we obtain 1 over square root 2 pi np cube for p tilde. And by substituting this into this expression and using our approximation in the limit square root npq is much greater than 1, we can write it in the expression given in III. And now we're looking at the fractional error. What is the approximate value of p of n when n is around n tilde obtained by this expression minus the most probable value of p divided by the most probable value of p, that is the fractional error. And we find that for z close to 1, for example, this is basically of the order of 1 over square root npq. If p is equal to q, on the other hand, then we have the z square term remaining, and for the exponential of e to the minus 1/2 z square, for small z we can use the expansion of the exponential for small x. So we have 1 plus x squared over 2 factorial, so that is here 1 minus 1 over 2 z square. And by substituting for z square, n minus n tilde square over n capital NPQ, we see that the error is now of the order 1 over capital NP